Hi, welcome back to LeetCode. So in this video, I'm going to discuss LeetCode problem 3604. Minimum time to reach destination in directed graph. So you are given an integer n and a directed graph. Okay, so that means u to v. I can go from u to v, but we can't. This is not true. From v to u, this is not possible, right? So with n nodes level from 0 to n minus 1, this is represented by a 2D array edges, where edges I represent ui, vi, start I, end I indicates an edge from node ui to vi that can only be used at any integer time t, such that start time of I less than equal to t less than equal to end I. So that means suppose I can reach from 0 to 1. Our start time here actually it is suppose 5 and end time it is 10. So at time t is equal to 4, can I use it? No. T is equal to 6, can I use it? Yes. T is equal to 10, yes. But t is equal to 11, can I actually use it? Not. No, right? So you start at node 0 at time 0. Okay. So in 1 unit of time, you can either wait at your current node without moving or travel along a outgoing edge from your current node. If the current time t satisfies start I less than equal to t less than equal to end I. Okay, we have written the minimum time required to reach node n minus 1. Okay, if it is impossible, return minus 1. Okay, so what is the brute force approach we can think? So DFS extra we can actually think DFS approach. So that means we will start from 0. Current time is also 0, right? So first of all, I actually have one adjacent list like from in this example 1. So that means from 0, this actually u, v is 1. So from 0 to 1, I can go at the time 0, 1, right? And from 1 to 2, I can go at the time between 2 to 5. Okay, right? So I will be at the cell or the node 0 at the time t is equal to 0. Now I want to move to the next adjacent cell. Next adjacent node will be what? 1. Alright. So what is the time? Current time is 0. And what is the time to use this edge? It will be between 0 and 1. Can I actually use this? Yes, because the current time is greater than equals to 0 and less than equal to 1, right? So this actually I can use this edge now. So I'll move to the next this node 1 at the time 1, because it will take 1 unit time to traverse the edge. So I was actually at the node 0 at t is equal to 0. So I'll be at the node 1 at the time t is equal to 1, right? Now from this current node 1, for example, I can go node 2. So what is the time it will take? So current time is 1. Can I actually use this? When actually I can use this edge. So it will be like I can use only between 2 and 5. But our current time is actually 1. So I have to wait till t is equal to 2. So it will take actually at t is equal to 3. I will be at the node 2. Clear? Because I can only start from 1 to 2 at the t is equal to 2. So I have to wait from t is equal to 1 to t is equal to 2. So this will actually wait, right? So I can reach the node 2 at the time t is equal to 3. So that's why there is only one path. So that's why output is 3. So what is this actually the brute force approach here? So I will actually have the starting node 0, current time is 0. So suppose this actually helper function. So from this I actually have the adjacent list of node 0. So I can go from the node 0. Suppose first of all I got one adjacent node v1. So I know what is the current time. Current time actually it is 0, right? So I'll check what is the start time. Suppose s1 and the end time is e1. So if t is less than s1, that means what will be our time to reach v1? It will be s1 plus 1, right? right? If our t is greater than e1, can I actually use this? It is not possible. I will not be able to continue. But if it is t is greater than equals to s1 and t is less than equal to e1, that means I can actually use this. So whatever the current time actually I have, so I'll reach at the next node v1 at the time t is equal t plus 1, at the time t plus 1. This is clear, these three conditions. When our current time is less than the starting time of the next node or the current edge, whatever you are trying to say, both are actually same. So if the current time t is less than the starting time of the current edge, so I have to wait. So honestly, I will reach the next vertex v1. I will reach at the time s1 plus 1, because I will start traversing at the time s1, and it will take one time. So I will reach the next node v1 at the time s1 plus 1. This is clear, because I have already reached the destination, the starting cell. But to use this edge, I can suppose you can also mention that the train. So a train will start from the suppose 11 o'clock, but I have already reached the station at the 10:50. This is possible to get any train. This is not possible. So that's why I have to wait from 10:50 to 11, right? So that's why it will only start from 11 o'clock only. So that's why it will only start from s1, right? And when actually I reach the next node, it will be take 1 minute, 1 second or 1 unit time of. So it will reach s1 plus 1. This is clear. Now I have reached after train has left the station. Is it possible to get any train that time? Not possible to get this current train, because I have reached after the ending time. That means t is greater than e1. So this is not possible. I will go to the next adjacent node. If our current time is in between, t is greater than equals to s1 and less than equal to e1, so I am actually on time. So when actually I will go to the next node v1, I will reach at the time t plus 1. Clear? So in this actually I will explore all the adjacent nodes, and I will want to check that what is the current. Whenever the current cell is equal to n minus 1, I will check that what is the current time of that. So that will be our one possible time, minimum time to reach the destination or node n minus 1. So in this actually way, I will explore all the path. Suppose let's draw an graph. This is suppose this actually the target 0, 1, 2, 3, 4, 5. So this is actually source. This is source, and this is actually destination. So first of all, I am starting from here node 0. So suppose I go to the next node actually 1. So I'll check before going to the next node 1. I have to check that can actually use this edge or not. So when actually I can use, suppose here actually I reach at t is equal to 0. Suppose here actually I reach t is equal to 2. Suppose, because here actually I can use only 1 to 2. Suppose, so I have reached at time is equal to 0, but I can only start the using from t is equal to 1. So this is not possible. I have to wait till 1. So I will reach at the t is equal to 2. Again, suppose here actually I can, from this path I can reach t is equal to 5. Suppose in the destination. Okay, this is one. When actually reach the destination, d is current node is equal to 5. So I will actually compare with our answer. So our answer will now it will be actually the one possible time, actually minimum time will required 5. Okay. Next I will explore the next path. So next path it is this. Suppose I have reached this node 2 at the time t is equal to suppose 3. Okay, this is possible. Suppose here actually I have reached t is equal to 6, and in this and from this node 3 to node 5 I have reached t is equal to suppose 8. So what is the total time required in this path? If I want to reach the destination node 5, it will take 8 minutes suppose. So but I have already explored one path that actually minimum compared to the current time. So this actually still it will be 5. Okay, next I'll go to the next path. Next path will be what? So next path will be till this actually 3. This is clear. T is equal to 3. I will reach the node 2. but there is one more adjacent node for the node 2. It is actually node 4. So suppose I reach here at actually t is equal to 4, suppose. Okay, this path actually clear. Now from this path I can actually reach, suppose t is equal to 5. Okay, in this path it will actually take t is equal to total 5 minutes. Actually in this path it will take actually 5 minutes. So this is one, and in this path it will take t 8 minutes. So ultimately what is the minimum answer? It is 5. So in this we can actually export that. So it will take like all the paths. So I have to visit, like it may possible that this situation is possible. So this is possible that in this, how many path I will explore, I will visit this node twice. So this repeated situation is possible. So that's why I have to explore only the, so it will take exponential time consider, right? Because each node u actually have v number of adjacent nodes, suppose each current node u. So again from the next node actually it will again some number of actually adjacent nodes. So it will actually take exponential. Clear? So this will give us TLE. Now how can I actually optimize that? So I can use the Dijkstra algorithm here. How? So here we have to modify that direct. We can't actually use the direct Dijkstra algorithm. How? So suppose we actually know that time t is equal to 0. I am at the node u. Okay. So I will use the priority queue. Minimum priority queue. Why minimum priority queue? Because I want to reach the destination at the minimum time. Correct? Minimum time I want to reach that. Now for that I will actually take the time map. So actually I will reach the node 0, node 1, node 2, node 3. In this actually I will check. So initially all I will initialize with infinity, positive infinity. Okay, I have to minimize that. So what I'll do, so I will start from the node 0. So I will at the node 0 at the time 0. Okay, so I'll modify that with 0. So in the queue, what will starting node actually we will have, I will actually have time 0. I will be at the node 0. Correct. Next I will explore all the adjacent of 0. Okay, so I will know the current time. In I am at the node 0. So suppose from 0 I can go 1 or 2. So I will know for this edge what is the starting and ending, and I also know the current time t. So I'll check that when actually I can reach the node 1. So if the explore path, whatever the time actually it will take, suppose t1. So I will check that is it actually based. So still it is infinity. So I'll modify with t1 and I will add this into our queue. Suppose it will be t is equal to t1 and I will add the node 1. Clear? Next I can go to node 2. So when I can reach the node 2, I can go suppose t2. I will be at the node 2. Okay, and I will check what is the best. So node 2 I can till actually now best actually I have infinity. So this is actually not best. So I will actually modify with t2. Okay, so in this now actually I actually suppose t1 actually the minimum time. So I will check that from 1 when actually I can go. Suppose 2, 3, 4. This actually I can go from the node 1. So I will check what is the next time it will take to reach 2. So if I have already mentioned 3 conditions, like if the current time is greater than e1, so I can't use this current edge, not possible. If t is less than starting time, so I have to wait for s1 plus 1. I can reach the next node only s1 plus 1. If our t is greater than equals to s1 and less than equal to e1, so it can only reach at the t plus 1, right? This condition is clear. So I'll check that each edge can actually go to the next node 2. So if it is possible to go to 2, so until the next, what is the time to reach node 2? So I'll check what is the time. So I'll check that is it best now. So if it is best time to reach the node 2, so I'll add this into the queue and also modify in the map or the vector to know the what is the best time to reach the node 2 or node 3, any one of the node actually I can say that what is the time it will take, minimum time. So in this I will explore all the paths until actually our queue actually have some nodes. So if it is not empty, I will explore the adjacent node of the current node actually I have in the queue. So after that, I will actually check what is actually the best time or best minimum time for the node n minus 1, because I want to reach at the node n minus 1. So it will actually know what is the minimum time it will reach to the this node n minus 1. Right, I have to return that ultimately. So this is the modified Dijkstra algorithm here actually I have used here. So if you don't know the Dijkstra algorithm, please first follow what is the Dijkstra algorithm. Then I think this condition actually it will be easy to implement this in this way, that I have to check that each edge it will be considered not. I have to know one more thing, that what is the current time, and when actually I can use the current edge. Right. So this is clear. So now go to the code. So from the edges vector, I have to create the list of the adjacent list, right? So that's why I have this actually 3D. 3D means there is n nodes are possible. For each node, I actually have many adjacent nodes are possible. So for each nodes, adjacent nodes, I actually have three things. One is the destination I can go, and the starting time and ending time. So that's why I have taken 3D vector. Clear? One, the key first, it will be indicate the starting node, and next list actually I actually have the V, S and E, or actually I can go. Right. So here actually you can see that I am iterating the edges. So this is directed graph. So I can actually only add, I need to only add the from U. So right, so adjacent of I comma 0, I am storing what? I comma 1, I comma 2, I comma 3. So this is one vector, and there are multiple adjacent possible. So that's why this is vector of vector. Clear? This is actually one adjacent node, but one adjacent node actually have three things. So that's why this is actually one vector, and multiple adjacent possible. So that's why this is vector of vector. Clear? So I'm storing I of 1, I comma 2, and I of 3. So this indicate the destination node, and what is the starting time? This is the starting time. This is the ending time. Okay. Now I have to take one vector of distance. It will indicate that what is the minimum time it will take to reach the current node. So there n nodes are possible. So that's why I have initialized with size of n, and I have initialized with plus infinity, long max, because I have to minimize. So that's why I have just initialized with positive infinity. So I will take one priority queue. So in the priority queue, what I have to store? I have to store the time when actually reach the current node, and one thing I have to store the when actually I have reached the current node. So there are two things: the time and the what is the node. Currently I will be present on the time. So this is pair of two things. One is for the time, and the next is the node. So I have what is the priority? What is the key for this priority queue? It will be sorted on the order of the time, because I want to minimize the time, because I have to explore the path that will take minimum time, right? Otherwise, in the DFS approach, I have already explored that, explained that why actually it will take exponential time complexity, because I have to explore all the path, because it may be possible that in next path it will, like first path I have explored the first path, it may be possible that next path I will get the better result, right? So that's why I have to explore that path also. But in the priority queue, if I always take the minimum time, so it will obviously at the end it will give us the minimum time only, right? So that's why I have sorted this in the order of the time it will reach the current node, and this is the syntax of the priority queue. And so I start from the node 0. They mention that you will start at the node 0 at the time 0. So that's why I will reach the node 0 at the time 0. So that's why node 0 it will take 0 time. So in the priority queue, what I have to insert, I have to store the time it will be to 0, and the current node it will be 0. Right? Till our priority queue is not empty, I have to explore the path. So I will get what things will I will get? I will get the t, the time, and the current node. So t and u. So I will pop from the queue, whatever the node actually I have, or the data actually I have in the top of the priority queue. And I will check that if our current time t is the time till actually I have explored reach the current node u. If it is greater than that, that means I have already explored, I have already found one better result. So I don't need to continue that. So I'll just return from here, continue, go to the next data, next node. Got it? Why actually returning from here? Because I have already explored one path that actually better than the current time, better current path. So I don't need to continue I don't need to explore the current path, correct? So else this actually best, one of the best paths suppose. So I will actually explore the adjacent nodes for the current node. So just that's why I am iterating the um, adjacent list of the current node u. So I'll get three things. One is the destination v, the starting time s, and the ending time of the current edge. So I'll check that if a current time t is greater than e. So that's why I can't take the current edge, because I reached the station after train left the station, right? So that's why we can't actually got the actual train. So that's why if our current time is greater than the e, so just continue from here, go to the next adjacent node. Else this is actually within our range. So I'll check that if our current time is less than s, because that means I have reached the station before the train will start, right? So that's why the next time it will take, it will be start from s only. Else I am reached the station at the intermediate, like between, so like I can go from 5 to 10, between only 5 and 10, but I have reached at the time 6, so start time will be 6 only, right? So that's why st will be 6. Else suppose I reach at the station 4, so I can start only 5. So that's why if t less than s, I can only start from s, means 5. Otherwise it is within the range, I will start from the whatever time which I reach the station, so it will be t. So the starting time will be st, and when actually I arrive the next or the adjacent node, it will take one time, so that will be st plus 1, right? So I'll check that if the time it will take to reach the next node v, so is it based or not. So suppose in the past I have already explored one path that will take minimum time compared to the current time it will take to reach the node v. So that's why I'll check that the current time it will take arrive, if it is less than the destination v, actually I have till now, actually I have the best time actually I have to reach the node v. If it is less than that, then actually I can actually only explore the current, I will only go to the next node v. So that's why I will modify the distance of v with arrive, the current time it will take, and I will store it into the current data into the priority queue. I will arrive the node v at the time this arrive time, and the current node will be v. So I'll store it into the priority queue. Got it? In this way, I will explore all the adjacent nodes for the current node u. So got it? After this while loop, I will actually have the distance vector that actually indicate that what is the time, minimum time it will reach to the any node, 0, 1, 2, 3, any node, but starting node is 0, right? Now I will check that here actually our destination is n-1, so I'll check that the distance of the n-1, if it is less than long max, that means we actually have found some path, valid path, right? If it is not equal to long max, that means we actually found some, like we have modified some data, right? If it is equal to long max, that means there is no valid path to reach node n-1, that time I have to return -1. They mentioned that time required to reach node n-1, if it is impossible, return -1. So impossible, when it will be impossible, like if it is still long max, after explore all the paths, if it is still long max, that means there is no path to reach n-1, that time return -1. Else what are the value actually I have stored in the n-1, I will convert this integer, because I have to return integer value, that's why I have stored in the long as a long value, but I will return that as an integer. Got it? I will return that value. Got it? This is clear. So I hope this is clear. If you found this video useful, please like the video, and if not subscribe, please subscribe channel. Thank you. Bye.